After the tone, state your name, followed by the pound or hash sign. Thank you. You will now be placed into conference. To mute your line, press *6. To unmute, press #6.
You can just put whatever you want. You can put Lorraine Riley. You can put anything else.
Or put Matt. Put Matt.
Hey, Matt.
The planet feed is there by the...
It should have an ID already there, right?
Yeah, we just need an access code.
I know, but it does have a user ID, right?
Yeah.
Okay, that gentleman's got to give you the password. I didn't write it down. That's the only thing you're missing, and you'll go.
Yeah, I'll give that to you right now, and then we'll get started, folks. So the attendee entry code, if you don't have it, is 9 capital N lowercase b capital N *74. So welcome everybody to our webinar on better spillway designs through computational modeling.
I just have it all. I know.
What we're going to do right now is, in order to reduce the noise and everything on the audio, since we have a lot of people calling in, there are about 50 people called in, we're going to go into lecture mode here, and so we're going to mute the phones except for the presenters. So I'm going to do that right now.
Did you just repeat the access code?
Just try to put in a...
The leader has turned lecture on, and your line will remain muted until the conference leader unmutes your line.
If you do have further questions, then I suggest trying to use the Q&A tab in your live meeting section. And we'll move forward from there. So please use the Q&A tab if you have further questions. For anybody who doesn't have the access code, the attendee entry code is 9 capital N lowercase b capital N *74. In terms of how we're going to answer questions at the end, we'll also use the Q&A tab at the top of your screen. Also, generally, questions come up about the availability of slides and recording of this event. We will be making those available, and we'll send out an announcement to everybody who registered about that. We will also make those available from the Alden Acres website. So our agenda today is, first we'll have an introduction to spillway safety from Mario Finnis at MWH Americas. That will be followed by 2 presentations on computational fluid dynamics tools. The first from Mark Horner of ANSYS, and the second from David Souders of Flow Science. That will be followed by a presentation on using CFD for spillway analysis by Dr. Dan Gessler of Alden. So now I am going to introduce Mario Finnis. He's the Vice President and Division Director for the Americas Northeast and the International Dams and Hydropower Group at MWH America. He has 26 years of broad-based experience in the energy and water resources sectors, including planning, design, analysis, inspection, economic and financial evaluation, rehabilitation, and construction oversight of water resource, power, and civil structural projects. He has a degree in civil engineering from Tufts University in Massachusetts and a master's in business administration from DePaul University in Chicago in 2000. He has completed the advanced management program at Harvard University that was finished in the fall of 2008. Mario started his career as a civil structural engineer in the nuclear power industry with Stone & Webster in 1982, and then moved to the hydro industry, joining Morrison Knudsen in 1985. Mario then joined Northeast Engineering Associates in 1988, and then Harza, now MWH, in 1994. And with that, I'll turn the floor over to you, Mario.
Thank you, David. I'm very pleased that you've all been able to join us today, and I have the opportunity here to talk about the subject that's near and dear to my heart, and that's dam safety, and in particular, issues related to spillways. As David mentioned, I'm going to give a brief overview of dam safety because our audience does have quite a varied background, and then my associates will get into some of the details of CFD modeling and the software use. The focus of this presentation is, of course, spillway safety. It's a very important aspect of the overall dam safety program, but I do want to emphasize that it is only one aspect of dam safety. All of these other factors are also very important to having an effective dam safety program. And the reason that's important is that, unfortunately, I have to say that dams do fail. One of the most famous failures that we probably all heard about is the Johnstown flood, which happened in 1889. And that was actually a spillway issue. There was blockage of the spillway that resulted in that failure. This photo here on this slide is the St. Francis Dam in California. This project, when it did fail, resulted in the loss of 600 lives. So both the upper left-hand picture and the lower right-hand picture are the same dam. So it is important that dam safety be treated in its full effect, and especially when it comes to spillways. More recently, there have been a series of failures that happened in the early and mid-70s that led to the passing of the National Dam Safety Act. And this was a program that resulted in the inspection of all non-federal dams, and really is what I'll call the impetus that led us to the modern era of dam safety. The program started in 1978, and dams were evaluated primarily for two factors, structural stability and spillway adequacy. There was a lot of rehab that was done as a result of those projects, and a lot of upgrades have been done over the years, but we're still not done with that yet. Just in case anyone thinks that a lot of this work has been done, we have seen recent failures here, including one of the more infamous recently, the Tom Sock failure in Missouri in 2005, which was a result of overtopping. So dam failures are still an issue even after all these years that we've spent resolving the problems that came out of that first identification program. Now that we know that dams fail, we might ask, well, how do they fail? The predominant mode of failure for dams is overtopping, and this is why the spillway issues that we're talking about today are so important. Overtopping can occur for a number of reasons. One, of course, is the spillway capacity just may not be large enough. And that could be due to a couple of reasons. There's been a series of changes in the way we calculate design floods recently, which has caused floods to actually increase from what the projects were originally designed for, and I'll get into that in a moment. Also, there are things like settlement of dam crests that can lead to having less available capacity in the reservoir, and thus a certain design flood may come and overtop the dam as well. So overtopping and spillway capacity issues are very important when it comes to dam failures. We've done a lot of work already, as I mentioned, but we're not done yet. We still see, even today, about 50 dam failures a year across the United States. And this is something that's going to be a continuing problem into the future. You see the statistic here that over the next 20 years, more than 85% of our dams are going to be 50 years old. So we have an aging infrastructure problem in the dam sector, just like we do in many of our other sectors. There haven't been a whole lot of new dams built recently, as you probably know, but even there we're still starting to see a little bit of change. There's some events recently that are causing this. There are more areas that we're getting water supply shortages, the southeast and certainly the Denver area are two in particular. And also water security. There's a project being done in California, several projects being done that are being designed to provide storage in the event that an earthquake terminates some of the pipelines that are traveling across the various faults there. So we are seeing some increase in new dams being constructed in the United States. So the next question we might ask is that what regulations might apply to our dams, either existing dams or new dams, when we're looking at designing spillways in particular? Well, that depends on a couple of things, and it's the type of ownership, whether it's a federal project or a non-federal project, and then the type of project itself, whether it's a power project or a non-power project. Power projects come under the jurisdiction of the Federal Energy Regulatory Commission, whereas non-federal or non-power projects would come under various other agencies, including state dam safety agencies. A lot of these approaches to dam safety and spillway design are similar, but there are some differences between them that do need to be taken into account. account once you've identified the appropriate agency that has jurisdiction. Now that we've decided the appropriate regulations apply, now we have to design the spillway. There's these three components to spillway design that have to be considered. First, of course, is what spillway is it we're going to design for. There are a couple of different factors that get into that, and I'll talk about those in a second. Another factor, of course, is once you've decided on what that flood is going to be, whether that's, say, a 100-year flood or a 1,000-year flood or some other flood, is the actual calculation of that design flood itself. And typically, the maximum flood that we design for is the PMF, or the probable maximum flood. And there's a hydrograph that goes along with that dictates the volume of water and the amount of water that comes over time. And then once we have both what we need to design for and the flood characteristics, then we actually route that hydrograph through our project. And that's where CFD can certainly come into play and help us with both the selection of the flood and the routing of the flood itself. Briefly here, I'll talk about the methodology that's been used to decide what flood we should be designing for. This is something that has changed in the past and actually may continue to evolve into the future. Originally, back in the early days, many of these projects that exist have been designed based on the largest flood that have been seen up to date. People figured that they would design for the largest flood that's occurred and maybe even double that, and that they shouldn't ever get a project flood larger than that one. Unfortunately, that didn't prove too correct, and we did have floods that have been bigger than previous floods that resulted in dam failures. More recently, we've gotten into some statistical analysis. As we've collected data on river flows and floods over the years, we've been able to do analysis to actually calculate something like a 100-year flood, or in some cases, particularly in the international market, they use the 10,000-year flood that's based on actually data that's been collected. There are some problems with that approach, which I'll get to in a second, but more, I guess, to the point for the more recent modern era, the Phase 1 program that the U.S. Army Corps of Engineers implemented as part of that National Dam Safety Act was really based on an empirical method. And I hope you can read this table well enough, but this is really an empirical design based on the size of the project, whether it's small, intermediate, or large, and also the hazard classification. Now, the hazard classification has to do with the setting of the dam, meaning if it's a dam that's out in a rural area and not much would be impacted if the dam failed, then it was usually in that low hazard category. But if it was one where it was in a more developed area where people could actually lose their lives if the dam failed, then you'd be in the high hazard category. So an example here might be a significant small dam, which would then be designed according to this criteria for either a 100-year flood or even the half PMF, depending on the judgment of the person doing the inspection. More recently, we've gone to this PMF-based approach, which is based on precipitation, and this type of approach is based on a deterministic method that really calculates parameters such as the ability of the air to hold water and runoff characteristics, and that's the method that we've used more recently. And where we're headed in terms of flood selection is really towards a risk-based approach. This was first suggested back in 1973 by an ASTE committee, but now we're really starting to see this take off, and it's really a site-specific approach that takes into account all the characteristics unique to that particular project location, and also unique to the watershed as well. So a lot of these projects that have been developed in the past, we are seeing changes in design flows that now cause us to revisit the project and actually develop new spillway designs. In this case, what's happened here is urbanization and development. As I mentioned, a lot of these projects are going to be about 50 years old here in the next few years. And a project such as this one in the photograph that may have been developed in a rural area when it was built, now if the dam were to fail, you can see that there's been a lot of new development downstream of it that would be impacted if the dam were to fail. So what this does is actually change the design requirements for the dam. And rather than be in what might have been considered a low hazard category previously, it would now fall into what's considered a high hazard category, meaning that the spillway would have to pass a lot more water. Otherwise, failure of the dam could certainly result in the loss of life. Our flood frequency analysis has also changed over time. In the intervening years since these projects were built, we've been able to collect a lot more stream flow data. So what might have been designed for 30 years of data, we might now have 60 or 70 years of data. And when you do that, that can actually change the magnitude of the design flood if you're calculating a 100-year flood or even a 10,000-year flood. Another thing that's changed over time is the actual amount of precipitation that we use in the watershed to determine what the flood might be. Here you can see the development of the various hydrometeorological reports over the years, starting with HMR 33 in 1956, and that's been updated over the years, and each time it changes, that has the potential for actually changing the requirement of the spillway to pass floods. Where this might be going in the future is still somewhat at risk here. With the events that have been taking place on global warming, a lot of people think that we're going to get more intense and extreme events. So that does have the potential for affecting our design floods as well. So once we've determined that we do have a change in our design flood, now we look at possibly remediating that. The CFD model that we've used, are going to talk about here, can be very valuable in a number of ways. Certainly routing that flood that we talked about earlier is the first step in the process to determine whether or not we actually have a problem with the new larger flood. If we do have a problem, then the next step is typically physical modifications to the dams. Here are just a couple of examples of that. The photo on the upper right, we've added some spillway capacity to the center of what used to be a solid gravity dam. And on the lower left, we have an overtopping protection project where we've actually armored the earth embankment with some roller compacted concrete. Anytime we talk about making these kinds of physical changes to a project, though, we're talking about quite a bit of money for the owner. And that's where CFD can play a very important role in helping us to optimize the use of these resources and getting the most cost-effective project for the owner. Now, CFD has come into play more recently for a number of reasons. I'll let my associates talk about some of the details, but with the increasing availability of computer power and the software that's been developed recently, we've been able to do this in a much more cost-effective manner. We were actually able to do these virtual models now to simulate the projects, whereas previously we would do this using physical models. Now, developing physical models was always a very time-consuming process, and once you developed even the physical model, it was very difficult to make changes in that model to do these what-if scenarios. If you're trying to modify a project for various different options to see what might be the most effective, having the ability to do that with a virtual model is a real time saver and cost saver as opposed to doing that on a physical model. This is just one example of where we're using CFD modeling on a project, and this is, I think, demonstrates some of the features where CFD modeling can really be important. This is a rather complex geometry for a number of reasons. We've got a stepped structure. We've got a curved section in our spillway. The channel's very irregular. The weir crest is also irregular. So when you have this many variables, it's very difficult to get an accurate representation of the model doing more traditional calculations. So this CFD model will really give us greater accuracy and greater confidence in the results. And certainly it's much faster and gives us a lot more capability to try different things in a virtual setting as opposed to a physical setting. So with that background, I'm going to turn this over to my associates, and they'll get into more of the details and the capabilities of the CFD modeling and the software.
Great, Mario, thanks so much for your talk. Very educational. I do want to let people know folks have been trying to log in or called in late and you don't have the attendee entry code needed to log into the live meeting, it's 9, capital N as in Nancy, lowercase b as in boy, capital N as in Nancy, star 74. I'm going to now introduce Mark Horner. Mark is currently a lead technical services engineer at ANSYS. He joined ANSYS after earning his PhD in chemical engineering from Northwestern University in 2001 and began by providing support and professional services for clients in the areas of biomedical, materials processing, and water industries. Mark now helps coordinate ANSYS business and technology development activities for the healthcare and water sectors in North America. Mark?
Well, thanks for the introduction, Dave, and thanks to Mario as well for the great introduction on the CFD part. Dave, are you able to forward the slides for me, or are you going to give control over to me?
I can, but you should have control down in the lower left-hand side with the up and down arrows, Mark.
Gotcha, thank you. Okay. So if everyone can see my first slide, I wanted to start off today with a few examples as a way to introduce ANSYS capabilities and experience in this area. For the example shown here, we see ANSYS fluid flow analysis tools can and have been used to model flow in a wide variety of problems relevant to the environmental and hydroelectric industries. Examples range from turbine modeling to draft tubes to the topic of today's webinar, which is spillways. And as you can see, our fluid flow modeling tools are comprehensive in that they are able to model free surfaces, rotating machinery, the presence of cavitation, turbulence, etc. And although not shown here, we are also able to couple our fluid flow mechanical analysis tools to model the interaction between fluid and structures. So this is my outline for the few slides I have today. First, I'll give a little background on ANSYS as an organization, followed by some information on the engineering analysis tools that we provide. Then I'll give a brief introduction to the computational modeling process, using a spillway example as a reference. Then I'll conclude. So ANSYS Incorporated was founded in 1970. We develop and globally market engineering simulation software and technologies widely used by engineers and designers across a broad spectrum of industries. We focus on the development of open and flexible solutions that enable users to analyze designs directly on their desktop, providing a common platform for fast, efficient, and cost-conscious product development from design, concept, to final stage testing and validation. ANSYS is headquartered in Canonsburg, Pennsylvania, and has more than 60 strategic sales locations throughout the world. ANSYS and its subsidiaries employ approximately 1,700 people and distribute ANSYS products through a network of channel partners in over 40 countries. So as far as our product offerings, over the years, ANSYS has systematically assembled a full range of simulation capabilities, ranging from structure to fluids to thermal to electromagnetics. All products are supported by a complete set of analysis types and wrapped by a unified set of meshing tools. These products are the cornerstones of the ANSYS portfolio, enabling our vision of simulation-driven product development. And then of relevance today, just narrowing down this picture a bit, are our two general-purpose CFD tools, which are known as Fluent and CFX. These solvers are alike in many ways. They're both general-purpose CFD codes containing fluid flow, heat transfer, chemical reaction, and multi-phase modeling capabilities, and can solve flow problems over a wide range of flow speeds. They both contain a wealth of physical models, including turbulence, phase change, particle-laden flow modeling, rotating flow models, fluid structure interaction, and more. The modeling capabilities of both codes can also be extended through the ability of including user-defined subroutines. So now going on to the CFD process itself. The first step in developing any problem is to develop a mathematical description, which includes the equations of fluid flow, heat transfer, mass transfer, etc. Primarily for today, I guess, we're really talking about fluid flow in particular. Another key component is a representation of the flow domain in a digital format. This may come from a CAD tool or created from scratch in a geometry tool. One also requires knowledge of the material properties and initial and boundary conditions for the system. The spillway example shown here is from one of our channel partners, Ingecyber. This shows a spillway geometry which has been divided into two because it is symmetric. The inlet is to the upper left of the image and the outlet to the lower right. The next step on the geometry side is to break then the domain up into smaller pieces, and we call these pieces elements. This process is typically performed using a meshing tool, and depending on the discretization, one either solves the conservation equations at the cell centers or at the nodes where each of these elements meet. The mesh and problem description are then sent to the solver and post-processed once the solution is obtained. A key physical aspect, though, on the solver side that we should talk about before going on to the solution is that we need to be able to accurately represent the height of the free surface throughout the entire domain. The volume of fluid, or VOF model in Fluent, can model 2 or more miscible fluids by solving a single set of momentum equations and tracking the volume fraction of each of the fluids throughout the flow domain. Typical applications include the prediction of jet breakup, motion of large bubbles in a liquid, motion of liquid after a dam break, and steady or transient tracking of any liquid-gas interface. And I just wanted to include one image at the bottom to kind of illustrate some type of validation. So this was an experiment which was similar to a dam break scenario where there's a column of water that's released at time 0. So we see on the bottom some digital still photographs that were taken by the experimentalists. And then on the upper images, we see the red fluid, which is free to move at time 0. So we see there's some pretty nice correlation between, the free surface in the experiment and then the free surface predicted by Fluent. Now, in this example, the transient form of the VOF model was used to compute a time-dependent solution. But for problems in which you're concerned only with a steady-state solution, it is possible to perform a steady-state calculation. Specifically, the steady-state VOF option makes sense when your solution is independent of the initial conditions, and there are distinct inflow boundaries for each phase. One example is flow of water in a channel with air on top, which is basically what we're talking about today in a spillway. So inputs to the VOF model include standard material properties. So we can input into the code, or users can input into the code, things like density and viscosity. And you also need to declare the boundary conditions for the problem. So this may be any combination of, 0 or no slip velocity conditions on the walls, the presence of a symmetry plane, as I showed in the previous slide for the geometry setup, time-dependent inflow conditions, pressure outflow conditions, and the like. The model, after you do this setup, then you can submit it to the solver. So, once we've submitted to the solver, gotten a converged solution back, we can start, post-processing that flow for the relevant flow metrics. And I'll just go through the next few slides, some typical examples you might want to look for. So in this case, what I show here is the speed of the water as you go through. And you may notice that there's a red box surrounding the word speed there. So what I did is just go through these 4 metrics that are shown, outlined explicitly here in the examples on the second line of text. So I'll show those, but certainly we can extract other material properties as well. So one result, as I show here, is speed. We can also look at the pressure distribution. We can also look at the fluid elevation in the spillway. So the fluid elevation is the distance from the bottom of the bottom surface to the water-free surface, and we can calculate this as each position throughout the flow domain. And then finally, we can also look at streamline plots, which illustrate the flow patterns in the fluid. So, there are certainly other things that you can extract, and you can also define, as I mentioned before, custom functions, which might be useful to extract things, other things that might not be native to the post-processor. So with that, that's the end of my slides. So hopefully today I gave you a good idea of what ANSYS tools offer. We certainly offer a comprehensive set of simulation tools that are broadly used and accurate. And our tools are well suited for modeling hydraulics problems in the environmental and hydroelectric industry. So again, I'd like to thank all of them for inviting us, and thank all the attendees. And with that, Dave, I'll turn it back over to you.
Thank you, Mark. Next in our list is David Souders, who's a mechanical engineer and director of sales and marketing at Flow Science Inc. David?
Thank you, Dave, and thank you, everyone, for attending today. And let me see if I can get my slides to work. Here we go. So first, I'm just going to give you a little bit of a company history and then go through my outline. Flow Science was founded in 1980, so we've been in business for almost 30 years now. And the development of our product actually began even before that, as work from the Los Alamos National Laboratories by the founder of our company, Dr. Tony Hurt. He came up with a number of numerical techniques for CFD and is the original developer of the volume of fluid technique. And at this point, Flow3D has now become a powerful general-purpose flow modeling tool that gives engineers valuable insights into many physical flow processes. And in this short presentation, I'll be focusing mostly on hydraulics capabilities. So looking at my outline here, first I want to talk a little bit about what is CFD and also how hydraulic structures can be optimized. And then from there I want to focus a little bit on time and accuracy, and these are both key components to simulation. You need to be able to set up your model quickly, get results quickly, and you also need quality results. And then on top of that, I'll talk a little bit about some of our advanced models, being a general moving object, and then some of our multi-physics capabilities, and then last I'll talk about post-processing that's geared towards hydraulics type modeling. So computational fluid dynamics, or CFD as it is known, is a way of predicting the behavior of real processes. And shown in these images are a couple of them. For instance, we're looking at a fish ladder at the lower left and spillway flows over towards the right. And what CFD does is it discretizes a domain, and that means it breaks it into cell volumes. And there are various means of doing this, and I'll explain how Flow3D does it as we get further into this. And then with that discretized domain, you numerically solve the equations of the governing physics. And for hydraulics, that's primarily going to be your Navier-Stokes equations and a continuity equation, and then your volume of fluid technique for free surface modeling. And what CFD ultimately does is it provides a virtual laboratory to test ideas and helps do things typically faster and less expensive than would be done with experiment. And it can also be very complementary to experimental work. So Flow3D's approach is what we call a hexahedral mesh or a structured grid. And with that, in our discretized domain, we take quantities at various locations. For instance, you can see here, and let me try the highlighter. Self-centered quantities, we look at pressure, temperature, and fluid fraction. Fluid fraction is what describes your fluid surface. And then your velocity components are on cell faces. And with that, we're also a staggered finite difference techniques. So we're taking derivatives across these cell-to-cell locations. And then on top of that, we also apply a control volume approach to ultimately meet continuity. And as you can see here, we also look at tangential stresses on cell surfaces, and body forces are cell-centered quantities. So then next, one of the questions would be, with a structured technique like this, how do we represent a complex geometry such as this shown at the left in a rectangular grid? And I will also address that momentarily. So how hydraulic structures can be optimized? Well, here are a couple examples. For instance, with fish passages, you could analyze critical components in the design of hydraulic structures, such as your fluid overall free surface profile, fluid depths. You can look at velocities throughout the depth and find out if they're reasonable enough for the fish to actually navigate the ladder. And then with dam and spillway performance, you can look at things like what configurations would best work, how does my stilling basin work, and the energy dissipators. And then you could look at things like flow rates for probable maximum flood conditions and find regions of cavitation and pressure loading on gates. So meshing. Meshing can be one of the most challenging parts of getting any simulation ready. And Flow3D's free gridding approach is what allows users to change mesh grids independent of geometry. And free gridding means that the mesh and the geometry are separate initially, and the preprocessor ties the two together. And our favor method, which I'll explain further soon too, allows us to do accurate calculations even in the presence of these complex geometries. And then shown here is a series of images as to how the meshing works. First, you import the geometry into Flow3D in STL and or topographical format. And then the user simply overlays their mesh blocks as shown in the upper right and defines a degree of resolution. And then from there, the preprocessor handles the rest and actually incorporates the geometry into the mesh, making it very automated and very simple. So favor is, again, how we handle these complex geometries, and it stands for fractional area volume ratios. And what we ultimately do is we integrate the conservation equations, the Navier-Stokes equation and the momentum equation into, or we integrate these area and volume fractions into those equations. And what we're showing here in this example is kind of an image of the imported geometry. And as you can see here, we block out those cell faces and those cell volumes, and ultimately don't allow flow into certain parts of the domain. The nice part of this is not only does it make the meshing real easy, but we don't have the momentum losses typically seen in a stair-stepped grid. Also, I want to briefly talk about free surface modeling. So free surface modeling is where you have a liquid-gas interface, and it's typically applicable to problems where you have a high density ratio. And a perfect example is a lot of this hydraulics modeling, where your ratio is about 1,000 to 1, and you're looking at water and air. And what that does is that means you can consider the pressure gradients and shear forces in the gas as negligible. And what this does is this ultimately allows for better accuracy in these type of problems and a faster computational time, because you only have to work numerically through the cells that have liquid in them. Shown here is a validation of our volume of fluid technique. And what we're looking at are a number of components that correlate well. And I won't go into the numbers, but I'll explain at least each quantity to some level. We're looking at the pool depth against the overall wall, or the overflow wall, I'm sorry. We're looking at the outflow depth at the domain boundaries of the far extents. And then we look at the pool length, which is important. It's the impingement point of the water overflowing into the pool at the base. We look at the nap angle, which is the approach angle of the water at the impingement point. And then finally, the overall energy loss, which is essentially looking at the difference between the kinetic and the potential energy from the upper left at E1 to the lower right at, actually I should say E2, but it says E1. Let me highlight that. This here should say E1. So then with that, to talk about some of our additional modeling capabilities, we have something that we call general moving object, and it's a 6-degree of freedom model, and it allows full 6 degree of rotations and translation, and on top of that, the motion can be coupled. It can be coupled by applied forces and applied torques, or some sort of partial constraint where it's fixed, perhaps translationally along an axis. And what I'm showing here is just a simple example of a tainter gate that's opening. Flow3D also has a very extensive number of physical models available. Here I'm just showing ones that relate to hydraulics type modeling. The first being free surface flows, which we already discussed. We can also look at sediment scour erosion, and in our next release to come out shortly, we will include multiple components of scour, so you could have different grain sizes, so to speak, and we'll be able to look at bed load transport, which would be kind of the overall bulk motion of sediment translating across the surface of the flow, or the bed surface. Also, we can look at air entrainment and bulking effects, and that means you can account for the volumetric changes as the fluid brings in air. We have flow rate boundaries to look at a volumetric quantity and a vector component to describe flow entering a domain. We can look at density variations, so along with our free surface modeling, we can also look at miscible and immiscible fluids and how they would mix and separate out. We also have phase change modeling, so we can look at vaporization and condensation. And then we have a fairly extensive particle model capability. And particles could be mass or marker. If they're mass particles, they would be fully coupled with the fluid. And then on top of that, in solid mechanics, as you've seen, we can do general moving object, where we look at fluid-solid coupling. And then also we can look at solid-solid collisions, where the user defines a coefficient of restitution and a friction factor. And then last, data output. We have a lot of data output that is focused on hydraulics modeling. So along with a full post-processor that does 3D views and data output and creates animations and images, we can also look at specific things like filling time or residence time. And residence time would be the total time the fluid remains within the computational domain. We can look at fluid elevation, and that would be your overall surface height. And we can look at fluid depth. Fluid depth would be the depth of the fluid from the surface to the floor bottom, or the bottom of the floor, or the bottom of the surface, and the distance traveled by fluid and vorticities. So that's it. Fairly brief demonstration. Again, I want to thank everyone for attending today, and I want to thank Alden for putting this together. And if you would like to schedule a demo of our product, please don't hesitate to contact me at the information shown here. Thank you.
Thank you very much, David. Next on our list is Dan Gessler, who's going to talk a little bit about CFD applications, looking at spillways. Dan has a PhD in civil engineering in hydraulics from Colorado State University. After completing that degree in 1995, he spent 7 years at Colorado State as a research scientist before joining Alden in 2002. At Alden, he served as the Director of Numeric Modeling in the Massachusetts office and now serves as the Director for Colorado Operations in the new Colorado office in Fort Collins. Dan?
Thanks, Dave. All right, for those of you that aren't familiar with Alden, I'm going to give you a very brief overview about the company, and then we'll move on to talk a little bit about how we use CFD for spillway modeling. Alden is the oldest hydraulics laboratory in the United States. We basically have 5 areas of specialization now, including hydraulics, and all of them, as you'll notice in a moment, in one way or another relate back to fluid mechanics. So we have a calibration laboratory, and they specialize in calibrating flow meters, and you see a picture here of our calibration lab. It's a fairly large lab, so they can mock up necessary upstream piping to calibrate unusual flow meters or flow meters that might not be installed under ideal conditions. We have an environmental services group that primarily deals with environmental issues related to water or water flow. So in this case, one that might be of interest to this group would be our fish passage, fish exclusion capabilities in keeping fish out of turbines for downstream passage and designing fish ladders and fish lifts for upstream passage. We have an air and gas flow modeling group, and they primarily work in air and gas flow problems related to the power industry. What you're looking at there is a CFD model of a wet stack scrubber. And then we have a field services group that basically supports the other groups in collecting the necessary field data that we need for the model. So that can be bathymetry, those can be velocity measurements, dye dilution studies, LIDAR, all of those capabilities that one needs to be able to do the type of numeric studies that we're talking about. And then finally, we have the hydraulics group, and that's the one that we're probably is of most interest today. So we'll talk a little bit more about that, hydraulics at Alden. One of the areas that we work in is dams and spillways. And at Alden, we basically have 2 ways that we can look at dams and spillways. One is with physical models, and historically, of course, that's how we have done this until recently when CFD was invented, or became more widely available, I should say. And then the other approach now is numeric modeling, as you can see in this picture on the right. So I guess we could, the numeric modeling of structures, we could break down the structures that we look at into 2 categories loosely, maybe, and call them new structures or existing structures. On a new structure, we would use CFD typically to pre-screen a number of alternatives and see which ones are going to be best suited, and then that alternative would likely be tested in a physical model depending on the risk associated with that particular design. On existing structures, going back to what Mario said earlier, there's a lot of existing structures where there's changes in the design flow for the various reasons that he highlighted, and those can result in the potential need to make changes to those structures as well. And there we use CFD to first model the existing condition and then model proposed conditions or proposed modifications and see how those are going to work. Other areas where we've used CFD on spillways has been forensic type applications where a spillway might not have quite performed the way as was expected. Then we went back and used CFD to try to reconstruct what happened and why a particular spillway may have failed the way that it did. And then, of course, the next step after you figure out why it failed is to make the necessary improvements. In each of those cases, we try to validate our CFD models either with prototype data, if it's an existing structure, or the physical model from before that prototype was built. And I'll show you an example of that where we went back and used an original model study to validate a numeric model. So I guess at Alden you might ask, why do we use numeric models? And it really comes down to what the other three speakers have talked about. It's typically less expensive than a physical model, and it makes a very good screening tool to reduce the number of physical runs that we might need. It takes less time to complete generally than a physical model, so it's less expensive and it allows us to consider more alternatives than what we might do on a physical model. Other things that benefits to the numeric models is if you want to try to create a velocity map or a shear stress map of a stilling basin, for example, you can certainly do that with a physical model if you collect enough data. In the numeric models, if you get your spot validations of the model and you're convinced that your model is correct, then that can be done probably more quickly than what you could in a physical model. There's other aspects of flow fields that can be difficult to measure experimentally, and if we can validate our models, then we can just go ahead and use the numeric results rather than trying to figure out how to make a very difficult experimental measurement. So the type of results or output that we generate that we tend to use a lot of at Alden would be stage discharge rating curves. We also use it to look at pressure distributions on spillways, and I'll show you an example of that in a moment that can be used in turn to calculate the cavitation index of a structure to see how likely it is that it'll cavitate. We use the CFD to generate three-dimensional flow fields. We can use it to look for and identify standing waves that can be important in terms of freeboard that might be available at a structure. We can use it to look at the air entrainment characteristics of a structure. We can look for hydraulic jumps as well. Now I guess I should point out probably the need for validation. I think everybody can appreciate that. The numeric tools are an approximation. And generally the CFD compares very favorable to the physical data that we've collected. Items that we've found that can be a little bit tricky sometimes to get right in the numeric models. We usually can get them right, but we end up using validation data to make sure that they are. Hydraulic jump locations can be somewhat tricky to predict in some cases. Stilling basin flows where there's extremely high turbulence, getting that captured correctly can be a little bit tricky. And then there's time-dependent aspects of the problems that are still being evolved, I think, in the CFD on how well that they can be captured. Things like if you've ever watched on a river, you can see boils appear and then disappear and then reappear. And it doesn't seem like the CFD always captures that entirely. But in many cases, those might not be things that you need to worry about. And then finally, I guess high hazard structures, you always want to be sure that the model is correct when you're dealing with one of those. So our first example that I'm going to show you is CFD, and here we use CFD to look at various approach channel layouts. I'm going to point out at this moment that Alden actually uses both Flow3D and Fluent. We have both codes, and we've found that in some cases one code works better than the other, and we basically just pick the one that we think will provide the fastest, most cost-effective solution. So let's take a look at Canton Dam. This one was also modeled physically. You're looking at the dam here. Let me see if I can get my pointer to work. This is the existing structure down in this area here, right around the number 10. That's where the flow passes through the existing dam. That dam does not have the necessary capacity to pass the the newly calculated flow, if you will. So a fuse gate spillway is being constructed on the side here, right in this area here. It's going to pass the extra flow without exceeding the allowable water surface elevations. What we used CFD for was to test a large number of different approach channel alignments as we come through this area here to find one that, one, gives us the water surface elevations that we desire, and two, tries to minimize excavation requirements. The two spillways are so close together that they are hydraulically linked, if you will, so a change to the fuse gate spillway will actually change the discharge coefficients of the existing spillway. We validated that model with a physical model, or better said, we tested our final design with the physical model, and you can see a picture of it here. It's a fairly large model, and this might go back again to what some of the previous speakers have pointed out. It's much easier to make a change to a numeric model than to break out concrete in one of these physical models and test a lot of different alternatives there. So ideally you try to test as few alternatives as possible in a physical model just because of the high cost of doing so. And then a picture here to give you an idea of what we looked at in the CFD model. And this doesn't capture the entire domain. The entire domain of the CFD model is what you saw in the slide 2 slides ago. But this slide is colored by velocity, and it's colored by, and it has contours of water surface elevation at the same time. And we can look at what the predicted water surface elevation is for a given flow. Second example that I'm going to show you of a potential of an application that we had is a evaluation of a flip bucket spillway. And the idea here was to see how are the spillways going to perform under greater than design flow conditions. So this is what the model looks like overall. There's two spillways, one on either side of the dam. And what we were curious, or what the client was interested in, is how are these spillways going to perform when the flow exceeds the design flow. For validation, this is one where we went back to the physical model study that we did back in the late 1950s. And what we can look at here, at least qualitatively, I'll try to use the pointer again here on the black and white picture, can look at how the water bulks up here at the contraction, and then if we get something very similar that occurs in the numeric model. We can also look and see where it strikes the catch chute down in this area here. We notice that we get a very similar, or basically the same spot where it strikes in the physical model. So at least qualitatively, the CFD seems to be doing a good job on this particular project. If we move on, we might want to look at this quantitatively. And quantitatively, we can compare the stage discharge rating curve for the facility. So in the dark blue line, you see the laboratory results, and then we need to correct those for viscous effects. So we get the green line, that's basically the corrected laboratory results for the stage discharge rating curve. And then the purple are the CFD results that match, I would say very closely, they're within 5% of the measured stage discharge relationship. And then from here, we went on and tested much larger flows to extend that stage discharge relationship up beyond what was measured in the laboratory back in the 1950s. The third example is more of a composite, if you will, from various studies that we've done, but that I can't show you specific pictures of. So what I did is I came up with a similar example that uses a standard design out of design of small dams. And what we're looking at here is the pressure on the surface of the spillway for cavitation purposes. And what we want to see is how does the pressure on the surface of the spillway change as the flow is greater than or less than the design flow. So you're looking at a cross section here through the dam. The dam is shown in gray, and it follows a standard OG shape out of design of small dams. If you're familiar with those, or if you're not familiar with those, you'll know that the shape of the OG here follows that of the underside of the nap. So right where the highlighter is here, the underside of the nap that you would get if it was just a sharp crested weir. So during the design flow, since the shape of the spillway is supposed to follow the underside of the nap, you would expect the pressures on the surface of the spillway to be just about 0, and that's at the design flow. So the first thing that we can do is see whether the discharge, as given by design of small dams, matches what CFD predicted. So the design flow for this particular one was 124 CFS per linear foot of dam length. And when we plugged in the same water surface elevations, we came up with a computed flow of about 123 CFS per foot. So we're within about 1% there, so we get pretty good agreement on the stage discharge rating curve. Then the next question was, well, how does the pressure vary with changes in discharge, go above or below the design flow? So we can put a virtual pressure tap on the spillway, basically in the area that I've shown here, right in this area here where it's shown by the red arrow, and see how that varies with flow. And I've plotted that here. On the vertical axis, I have pressure, and that's shown in feet of water column. And then on the horizontal axis, we have the discharge per linear foot of the dam. And then the design flow is the vertical red line. So if we look right in this area here, we see a slightly positive pressure at the design flow of about +3 feet of water column. And interestingly, as we move up on the discharge and we go about 20% above the design flow, we get a pressure on the surface of the spillway of about -15 feet of water column. The vapor pressure of water is at around -30, depending where you're at in terms of elevation. So at -15, we're going to start seeing some cavitation problems because of the roughness of the spillway. It'll actually cavitate at slightly lower or higher pressures than the vapor pressure of water. So hopefully I've shown you with this third example some of the things that we can look at with CFD using a very easily validated model, a model that if you wanted to convince yourself, you could also go to the Design of Small Dams book and recreate one of the problems out of there and see how well CFD does for your particular example. But the intent here was also to show that you can use this for non-standard designs. For a standard design, it's less interesting. For non-standard, when we start modifying structures, that's where the power of CFD really starts to come in. Obviously, we can also use it for looking at freeboard considerations as we look at existing structures or want to modify structures and see how they change with the changes in the design flow. So a quick summary. Hopefully I've shown you 3 examples on how we use CFD for some spillway applications. There are obviously many other additions or applications of CFD that I have not been able to show in the period of time that we have. And I guess the last point that I would make is that before you even start a CFD model, it's probably good to think about how the model is going to be validated or if it's going to be an unvalidated model. And certainly unvalidated models have their value in the industry, and I don't want to take away from that. But at the same point in time, we want to think about how we can validate the models whenever possible. So with that, I'd like to thank everybody for signing on and turn it over to Dave.
Yeah, thanks very much, Dan. And just a reminder to folks, if you want to ask a question, since we have so many people attending, it would be a little bit unwieldy to do that through the audio. So please submit your questions through the Q&A tab at the top of your screen. Just to give a quick summary, we talked about spillway safety. Mario Finnis talked about that and gave a very nice informative and introductory presentation on what the regulatory issues are and what people have to consider and how computation plays a role. Mark Horner from ANSYS presented on CFX and Fluent CFD tools. David Souders presented on Flow3D, and Dan Gessler talked about some applications of using CFD for spillway analysis. So we're ready now for questions. I've also left up everybody's, all the participants' email addresses in case you want to ask questions privately. One excellent question that came up during David Souders' presentation, but I think was also partially addressed by Dan's last point. can we tell our clients that they could totally forget physical modeling because our numerical models are good enough? So since this was initially addressed to Dave Souders, I'll let you take a crack at it first, Dave.
Okay. I would, in many cases, I guess we have validations that exist, and perhaps those could be applied. Whether you could totally do a simulation and ignore evaluation or validation, I think, is probably up to the specific project and the needs.
Dan, do you want to say anything about that?
Yeah, I think I basically agree with what Dave said. It really, I think, comes down to the individual engineer that's ultimately responsible for that project, and that probably is going to include some assessment of the hazard of that particular structure.
Any other comments, Mario or Mark?
This is Mark. So I'd throw in, too, that it comes back to experience as well. So at Alden, you guys, I'm sure, have developed so much expertise over the years. You already have a good idea of best practices, et cetera. And once those are established, I think people tend to be more, I don't want to say liberal, but feel freer to use it with less and less validation as time goes on. So once you're able to identify best practices for a class of problems, then it's typical to use those more and more and not rely as much on the validation.
Thanks. Next question. Have any of the presenters attempted to address issues with gas entrainment resulting from water passing over spillways, typically due to the velocity of the spilled water entering the pool at the bottom of the spillway? Dan, you mentioned that a little bit. Maybe you could take a first crack at that question.
Yeah, we've used it qualitatively to look at air entrainment or gas entrainment going over a spillway and then see where it goes in the stilling basin subsequently. We have not quantitatively validated those calculations, though. I know that David probably has something to say about that because I think they have done a validation with gas entrainment, so I'll let him talk about it as well.
Go ahead, David.
We have. I can't recall off the top of my head if we validated a spillway exactly, but we do have at least 4 validation cases of various scenarios, and we look at it both qualitatively and quantitatively, and have measured the quantitatively we have measured the volumetric effects, so the actual bulking. I'm sure if anybody wants that specific or those specific validations, I can find those.
Great. Any other comments on that, Mark or Mario?
Yeah, maybe similar here. I could try and dig something up, but certainly we've gone through validation on multi-phase modeling in general.
Good, thanks. There's a question here about experience with gated spillways using Flow3D, and does it compare well to physical model results? And I guess why don't we expand that to include Fluent as well? And I guess why don't Dan, I'll let you take that one first, and then each of the software vendors too.
Yeah, I'm going to say that, I think all the spillways I've looked at have been ungated structures, so I can't say that I've actually compared a physical model gated spillway against a numeric model. So with that, I'll turn it over to David, and then I guess we'll say Mark and see if they have any validations.
Okay, thanks, Dan. I know we have a number of validations on our website available for download, and definitely for various types of spillways. I can't think of a gated case off the top of my head, but certainly a number of other designs, and it is possible that something's there. Again, I can't think of one off the top of my head, though.
Same here for Mark. I can't think of one yet. The gate one I could find easily. The ungated one I could find easily, but gated I can't myself either. Quote for
okay.
I guess I will add this. Gated is pretty standard design. You can probably fairly easily look up what those flow characteristics look like and design the small dams and run a fairly quick and easy validation.
Okay, great. Well, I think we're about out of time. We've actually gone a little bit over, so I appreciate everybody's patience. Thanks to all the presenters, and thanks to everybody for attending. If you have questions, you have everybody's email address here. We'll also be sending out an email telling you where you can get slides and a recording of this webinar. Thank you again.